Hi, here's another video on blockchain security. This is episode 6 of this current series, and it's about trade-offs. So whenever we design a system in engineering, there's usually trade-offs involved, and there are some trade-offs that affect the security of blockchain solutions. So the first one is quite obvious. There is clearly a trade-off between usability of a solution and security. Now, if we look at key management as an example, so you can either work, with cold wallets, air-gapped key management systems, and hardware wallets, or you can have like in-browser solutions such as MetaMask and much more easily accessible solutions. Of course, the former is much more secure, but it's also hard to use. If you want to deal with a hardware wallet, imagine you have to interact with a decentralized application. So you first have to create the keys on hardware wallet and write down some mnemonics words, and then whenever you use it, you have to plug in a device. You have to enter PIN. And it's just inconvenient. On the other hand, if you want to quickly interact with an application using something like MetaMask, you have your keys stored in the browser, where they're actually obviously less secure, and in most cases you don't even have to enter your password. You just click a button, or you have to enter your password like once a day or something like this. So much more easy to use, but also less secure. So in terms of dealing with keys in general on an end user level, my recommendation is always to have 3 levels of security. It's like I personally use MetaMask for interacting with Ethereum, but I have very small amounts stored or secured with these keys. And it's just, for interacting with a blockchain on a daily basis and paying transaction fees. Should I lose these keys, they're not used for anything sensitive. And then, I have a mobile phone for like a mobile phone wallet for payment scenarios, and the keys that are stored in there, they secure a larger amount of funds, bigger amounts, but it's still something, I could live with if it was stolen. And then there's the hardware wallet for savings and keys that I use to interact with highly sensitive applications. And in terms of enterprise applications, there's a similar solution. There's similar solutions, similar trade-offs to be made. And in terms of, if we step down to the protocol layer, or choosing a platform for our application, then there's an old theorem from the world of distributed systems research that we have to consider, and that's called the CAP theory. And that basically means that there are 3 properties which you only can have 2 of at the same time, and they're called consistency, availability, and partition tolerance. And it's mathematically proven, but it's also very intuitive that you can only have 2 of these properties. Partition tolerance simply means, poor network communication, so sometimes some nodes get separated and then the network is not completely reachable. Basically, we have partitions, parts of the network that cannot communicate with each other. And in that case, you have to choose either availability, i.e. continuing, or consistency, which means stopping in this case. It's like if you have 2 parts of the network that don't communicate with each other in a blockchain, you have to stop accepting transactions if you always want to be consistent on either side. It's logical. Bitcoin, for example, and Ethereum take the other approach, right? They favor availability over consistency, which just means that we can have forks in the blockchain, occasional forks where part of the network supports one version of history and another part of the network supports another, and eventually the strongest chain always wins. But because we have favored availability, because we are continuing, it can happen that a transaction is undone after it has already been included in a block. That's the reason we are usually asked, well, it's usually recommended to wait for 6 blocks at least before we consider a transaction confirmed. So that's about an hour in blockchain. An hour in Bitcoin. Because we have favored availability, we have to wait an hour to be completely sure. And again, there's a trade-off here, right? If we're just having a small payment, we can risk things. But if there's a larger transaction, we might want to wait long enough to be absolutely sure. Other blockchains, for example, many of these consortium blockchains that know exactly how many nodes are in the system at all time and usually have better network connections or more, or they know what the network conditions are like. They favor consistency over availability. Also, in the world of public blockchains, the example would be Tendermint consensus, used by Cosmos. In that type of system, consistency is favored, and if network conditions are poor, then we just have to stop. We cannot confirm transactions anymore. On the upside of this is, of course, that once transaction is included in a block, it's considered final. So there's instant finality in that case, if the network conditions are good, which means we can always consider confirmed transactions as final. And that's, of course, a property that might be useful for some blockchain applications, and availability might be a property that is more important for other blockchain applications. So when we are looking for a platform for a blockchain application or tokenization solution, we have to take this into account and make a decision based on what we need, consistency or availability. Quite related to this, relatively similar, is what is often called the blockchain trilemma. And that basically consists in another 3 properties: security, decentralization, and scalability. And again, it's very difficult, almost impossible, to achieve all 3 at the same time. If we look at Bitcoin, that's centered around here on this triangle. It's very secure in terms of the protocol, and it's extremely decentralized. It's probably the most censorship resistant and decentralized you can get with current blockchain protocols, but it's also the least scalable, right? We can have about 7 transactions per second on a global scale, which is almost nothing, right? So that scales particularly badly. On the other end of the scale, we have some things like EOS, which are fairly centralized, just a very small number of validators. Could also be argued that they've made some compromises on security compared to other protocols, but very scalable. And this is a trade-off that is difficult to get around. Ethereum 2.0 is trying to find the compromise, balancing all these 3 properties, but it's essentially a trade-off. Delegated proof of stake, for example, you reduce the number of delegators or validators to a known number of, not a small number of the validators, and that's got to be more centralized. But it also means we can execute very efficient very efficient consensus algorithms, making the whole thing more scalable. That might be necessary for some blockchain applications and the necessary trade-off. And we always have to look at what our application requires in terms of scalability and security and decentralization in order to decide what platform we choose. For example, a global payment network probably needs a very high level of security, whereas a computer game, just moving small funds around, doesn't. So it just depends what we need, and we have to deal with these trade-offs. Anyway, so that's it for episode 6 of this series. If you want to look at the previous videos, they're all on YouTube and their playlists. Also the other series on smart contract security and the introduction of blockchain in general are on there. So please have a look. I'll be back soon with another video.